value theorem. Let's start because it's also part of this. Before the mean value theorem, we will have a different version. I can say different version of the mean value theorem, and it is this is the Rolle's theorem. Is the name, of course, one of the mathematician's name, Rolle's theorem. And what this theorem, what this property is trying to tell us? If we have a function f, which this function must satisfy the following three hypotheses. Function must be continuous on the closed interval. Function must be nice and smooth, which this means differentiable on the open interval, of course, because we never have derivative at the endpoints. Continuity, differentiability, and also the third condition, the end values f of a and f of b are the same. If we have this situation, then if function is satisfying this condition, we can conclude and we can say that this is the guarantee for the number c exist in that interval from a to b with the condition f prime at c is 0. F prime at c is 0, it means that we have horizontal tangent at that c. Right? Oh, I do have a graphs, but I can maybe plot it. Okay, we need something like this because we need a and b to be the same. The values f of a and f of b to be at the same level. Okay, f of x, definitely continuous, definitely differentiable because we don't see any corners, any gaps, any jumps. And we can definitely spot, if we will have this condition, we will always find a point C where tangent is horizontal. And that point C, it will be always between A and B. Sometimes we will have such a complicated function that we will be not able to even find exactly that point C. But what we will know that if somebody will ask you, like, please put this number C on the number line, then you will know, oh, this value C is definitely between A and B, because that's the condition. And of course, derivative at C is 0. That's the condition. If the function is relatively easy, we can find that point C, we can calculate, but we don't even have to. This is just telling me that this number exists. And we do have in mathematics something like existence theorems, and this is one of them. Like satisfying this, and this, I can say, okay, the function is satisfying this condition, this condition, this condition, then it's definitely guaranteed that this number with of course, that condition exists. Okay. What I can also do, having this closed interval from A to B, I can try to connect these points. If I connect these points, since they have the same value, what kind of line I am creating? Am I creating like a horizontal line? Because the level, the value is the same. That means connecting these two red dots. Yeah, Michael is, that's okay. That's another one because you did connect this with the green line, which yes, okay, good. I will do this. But at the moment, I was just referring that when I connect these two, let's say blue dots, they are at the same height, I will always create a horizontal line. And now, yes, if this is horizontal line, the blue, the green is also horizontal because slope is 0, horizontal line, they are parallel. If they are parallel, yeah, in this case it's obvious, but even if the slope is not 0, but if they are parallel, they have the same slope, of course. All of the parallel lines, they have the same slope. Okay, and what is my point? My point is that the blue line, actually, it's connecting A and B, and theoretically represents the slope of the secant line, because connecting 2 points is the slope of the secant line. Slope of the secant line, I can say this is secant line. And this is, of course, tangent line. Tangent line. Yeah, secant line, tangent line. And it happens that they are parallel. They have the same slope. They have the same rate of change. And also the secant line represents the average rate of change. Yeah, it's zero because we can see the line is not changing, it's horizontal, it's not rising, not falling, not the secant line represents the average rate of change between A and B. The tangent line represents the instantaneous rate of change at C. And they end up to be the same. And of course, the conclusion is with this condition, the average rate of change between A and B is exactly the same like instantaneous rate of change at some point on that interval A and B. Yeah, that's the main point. But what we will do, this is just the special, like a special type of this mean value theorem, which I will show you in a minute, because now we can take these lines, we can take this situation, and they don't have to be horizontal. I can move them a little bit. Yeah, and for the mean value theorem, we have exactly the same condition. We just don't have the last one. Yeah, because I can change f of A, f of B could be at a different level, but I will still try to connect them, secant line, average rate of change, and I will be still able to find a tangent line with this parallel, with the same slope. So that's the idea. Average rate of change, it's exactly the same like instantaneous rate of change at some point in that interval. Okay, but now we still have the condition for the Rolle's theorem. Okay, and I do have a couple of examples. Like we can see this is between A and B. And the pink line represents the tangent line and at the point C. And each point C falls in the interval A and B. And we can even have two of those points. Yeah, we can see. We can, yeah, because if we have more, the situation, we can even have two. If it's the line, it's just the same line. We have infinitely many of these points. And when I connect this line, of course, I will not maybe messed up, but we can see I'm connecting this A and B. That means I'm creating this like average, the secant line. But the pink line is important. Okay. Let's just see. We can try to verify this, that the following function satisfies the three hypotheses of the Rolle's theorem on the interval between 0 and 9. Okay? And what we have to do, we're looking at the function and we see square, we don't see the graph, but we see the formulas. Root function, square root of x minus 1/3 x. It's definitely continuous on the interval from 0 to 9 because the numbers are positive. It's definitely differentiable because derivative exists. And we can get the formula derivative definitely exists. And we have to check, actually, I type it. Or we have to check if this is right. If f of 0, this is correct, this is correct. If f of 0 is the same like f of 9. Did I type? Can we substitute 0? Square root of 0, 1/3 times 0, 0. Oh, what about 9? Square root of 9, 1/3 times 9. 3 minus 3. Okay, yes, this is correct. Okay, that's now what is the conclusion, because that's important. The value is the same. I don't know how this function looks like. I think I don't have a graph, but f of 0 actually is 0 and f of 9 is 0. I don't know, maybe again, something like this. I don't know, just this part. Okay, just maybe not necessarily in the middle. Let me just maybe something like this, just not really symmetric. But the point, of course, is to find a point C that derivative is 0. It will be definitely there, definitely, because we have to kind of create that kind of like a hill when we're going from one point to another, and this point has the same value. And what we can do, we can try maybe to find this point. Let's check. We can compute because it's not complicated. We definitely know that the point exists. Definitely C is placed between 0 and 9. Okay. Derivative. We need the derivative. Derivative of square root of x is 1 over 2 square root of x. Of course, I am fast with this. And derivative of 1/3 x is just 1/3. And we have to set up this derivative to be equal 0. And solution of this equation, it will be that value C. And actually, I'm interested if we will get the value between 0 and 9, yeah? Because we know it's nice, we know what we're expecting. Okay, what I can do, I can add 1/3 to both sides, I believe, and we can cross multiply. Because x equals to 0 is not in the, we're not including 0 actually. Because derivative, actually, we can see derivative is not defined at 0. But that's different, yes? That's if the derivative is not defined at 0, and function is defined at 0, that's the critical number. Probably is the endpoint. It's okay, we can have it. Okay, let's cross multiply. 2 root x times 1, 3 times 1. Let's divide by 2. And let's square both sides. 9 over 4. Oh, I think 9 over 4 is like 2 1/4. Yeah. 2 1/4. Yeah, I was right. I don't know exactly how the graph looks like, but I was right to push it a little bit closer to 0. Yeah, it's definitely, and this is that value C. Yeah. But again, this theorem is like it guaranteed that point, which sometimes we don't even have to compute exactly. We know that it's between 0 and 9. 0 and 9 is quite long interval. Sometimes we will have tiny intervals and we will know that the point is between with this condition. Okay, we did this one. We will skip this for a second. We don't have to. We will skip this. Okay, you can check. Okay, no, we will skip this. Okay, so now that I tap, now this is the other version, the more general, I can say, the mean value theorem. And we can see it's the same idea. We'll really need continuous function and differentiable function. Continuous on the interval, the closed interval A and B, differentiable on the open interval, because we do not have derivatives at the endpoints. And now again, existence theorem. Check, check. If we have this condition, there is a number C. I suppose to circle the verb is. There is a number C in that interval, and now is this condition. Yeah. Oh, I don't know, I did rewrite equivalently, but we don't, I just multiply. I mean, it is the same. I think the boxed form tells us a little bit more. Again, f prime at C, like the previously, derivative, yeah, or in general, instantaneous rate of change is exactly the same, like f of b minus f of a, b minus a, average rate of change. Yeah? The right-hand side is basically the secant line, the slope of the secant line. Previously was horizontal, was 0. I mean, I was just putting 0. Yeah? But now, since they are not at the same level, I can shift them. That means this is simply secant line and the tangent line. Slope of the secant, slope of the tangent. Yeah? Also good, I do have a couple of applications. I can show you like what this probably will be so obvious. Right? And this looks like, yeah, not really maybe helpful at the moment, but one thing that we can also realize, this equation it's like connecting derivative at the certain point and the value of the function a and b at some points. Even if we don't have, like, let's say we will be doing some experiment and we don't have exactly the formula of the function, but we have some values. Yeah, then we can connect a and b, we can find that slope, and we will say, oh, between a and b, we have definitely the value that the tangent line to the possible curve will be parallel, will have the same slope, like between, like maybe the other way, instantaneous rate of change. The rate of change at some point in that interval is the same like this slope, yeah, of the secant line, and we can compute secant line. Okay, we can even have the slope, the instantaneous rate of change, not having the point C, but we will know that the point exists. Okay, I have a couple of pictures. Oh, okay. And as we can see, similar things, but I shifted. That's me, especially the first graph. The value of A and value of B, they don't have to be the same, but it's the same idea. The blue line represents the slope of the secant, this. F of B minus F of A, B minus A. And definitely one point, or at least one. We have actually 2 points at the second graph. We can always find a point that we can draw a tangent, and tangent will be parallel to the secant. This is tangent. Okay, parallel, and parallel means they have the same slope, the same value, yeah, of the rate of change. Mm-hmm. And of course, the blue line represents the average rate of change. Yeah, like one of the examples probably could be the driving. Let's say I'm like, my average speed was, I don't know, I don't want to say, let's say 65 miles per hour. That was my average speed. Okay, and do you think this indicates that I was driving constantly 65 miles per hour? Of course not. I was driving maybe a little bit faster, maybe a little bit slower, but not. But since I'm assuming that my driving was constant, everything I satisfy, did I have at least one moment that I was driving exactly 65? Yeah, that means it's something similar. The blue line represents the average rate of change, average speed. But at least once, or maybe a couple of times, I was driving exactly 65. My instantaneous speed was 65. Yeah, that means that's the same thing, the same idea. Okay. Of course, I did type this example. For instance, if the car travels 180 kilometers in 2 hours, then the average speed, right? The average speed, of course, is the distance over the time, 90 kilometers per hour. Let me try. Kilometers per hour, but of course my speedometer must have reached 90 kilometers per hour at least once. Yeah? Doesn't indicate that I was driving all the time 90. No. Yeah? 90 sounds a lot, but 90 is about 75 miles per hour because it's kilometers. Okay, and yeah, instantaneous rate of change, average rate of change. That's how we can, yeah. And yeah, we have some information about the function, and we can obtain some information about the derivative. Okay, let's see how we can use this property, mean value theorem. Oh, okay, let's do this. You will tell me. Let's get ready, and you will tell me the values. I can just say this is y, and this is x. 2, 3, 4, 5, 6, 7, 8. Okay, and we just want a function between 0 and 8. Use the graph of f to estimate the values of c that satisfies the conclusion of the mean value theorem for the interval between 0 and 8. Okay, connecting 0 and 8. Oh, not good, not good. I could be more precise. Okay, better, better. Okay, I mean blue line, of course, the blue line represents this, f of b minus f of a, b minus a. And I can be even more precise. I can say f of 8 minus f of 0, 8 minus 0. Actually, we can compute this. What is f of? We can compute that slope, basically. 1, 2, 3. What is f of 8? F of 8 is 3, f of 0 is 0. Okay, I mean, we don't have to, but we can see we do have the average rate of change, 3 over 8, 3/8. Okay, and now, can you predict, or like looking at the graph, I hope it's big enough, where, like, can we estimate where will be the value C? Where is the value C that I can draw tangent line with the same slope? Basically like parallel. Where, like on this pink graph, where I can where I can draw a tangent, but the tangent must be parallel. Like, oh, Michael's 3.5, Diamond is say 3. So, yeah, I believe is somewhere. 3.5. I'm worried 3.5 will be horizontal tangent. Yeah, and I mean it's still good approximation, because and we just need the horizontal tangent will give us 0. 3.5 will be perfect for the Rolle's theorem. Yeah, if the points will be the same. But Michael said 3. Okay, let me try probably a little bit before 3. Still good, yes, good. What I can use color? I can use green. Okay, I will try to, Michael is, yeah, I think, okay, let me just draw it like, oh, do you think that, yeah, I think that even 3, maybe 2, yes, maybe 2 points, maybe my graph, I would say like, yeah, I would even say 2 and 3, 2.9, 2.9. I kind of, actually looks, I don't know, maybe even 3. I hope they are parallel. Yeah? But yeah, we can say 3. The point is, yeah, we can say this is 3. One of the values C is 3. And can you try to predict the other value, because we have the other part of the curve. Also, we have to draw a tangent, but has to be parallel. 6 will be not good number, because 6 will give us horizontal. Probably more than 6. Oh, actually close. What do you suggest? I need just, I can make this. Yeah, probably close. Yes, like I think 6 point, my drawing probably is, okay. Yeah. 5, 3, let's say 4, but yes, everybody is good. Whatever you will put will be good. I think 6.5, maybe I'm just, okay, but we know the idea. If we have this condition, we can always find this point. And of course, these C values are between 0 and 8, no question. Okay, that you will be good with approximating. Okay, let's keep working, because I have a couple of more questions. Let me, you can check this later. You can check this later. Okay, this one is not solved. The other one is solved. You will have the solution, you will understand. This is the same thing. Let's see, because this one I didn't type the solution. Find the number C that satisfies the mean value theorem for the function 9x squared plus 5x plus 6 on the interval between -5 and 5. Okay, definitely function is continuous and differentiable. As we can say, function is continuous because it's just parabola, quadratic function, and function is definitely differentiable, and we will never add the endpoints because we do not have continuous and differentiable. Then there exists a number c that derivative at c is the same like average rate of change between the endpoints. And I can, instead of a and b, I can substitute. Okay, we just have to find out this, solve this equation. Derivative the same like average rate of change. Of course, first of all, I can put x, and that x will be c. Okay, derivative is 18x plus 5. Yeah, I just differentiate a function. Now, we need value at 5. A little bit of calculation. Let's compute. 9 times 25 plus 5 times 5, 25 plus 6. 9 times 25 and another 25 is 10 times 25. 10 times 25 is 250 and 6. Wow, not bad. Now when I substitute -5, we will have again 9 times 25, 5 times 5, 25, but minus. 9 times 25 minus 25 will be 8 times 25. But 8 times 25 is just 50 less than 250, 200, 206. You can probably do a little bit slower or even faster, and you will also get these values. Okay, 18x plus 5 equals to 50 over 10. 50 over 10 is just 5. 5 minus 5, 0. X is 0. And 0 is perfect because 0 belongs to that interval. That means this value c is 0. Okay, I don't know exactly how this function looks like. I don't want to draw it. Ooh, the values are so big. Okay, 5 is 250, -5 is lower. Okay, let's say, I don't know, I'm just trying to, let's see this. Okay, maybe. At -5, we have value 206. At +5, we have value, I'm just trying to picture this situation. We have value 256. And the average rate of change, I can use blue. This, no. Okay, I thought that is, no, it's 5. Okay. For some reason, I thought that this is supposed to be horizontal, but no. At 0, I don't know if I can manage this, if my graph is good, but at 0, I supposed to draw, okay, not bad, parallel line, because x equals to 0 will give me that tangent line. F prime at 0 is the same like the slope of the blue line. Okay. And that's, of course, that's the parabola. I don't know exactly how this parabola looks like, but between -5 and 5. Of course, my scale is not, the labels are good, but the length of 5, it's even more than length of 206. Okay, but we do have the idea. Okay. Let's answer this question. Let me just check. No, did I type everything? Okay, but no, let's solve one of them. I thought that is empty slide. One more time. No, don't. Okay, I have this. I have the place here to draw it. Okay, let's see this question. I have 3 of those. Each of them is solved. It's okay. Suppose that f of 0 is -3. Okay, f prime of x is less or equal to 5 for all of the values of x. This is, of course, giving us information that derivative exists. Function is differentiable because it's telling us that even we have some information, f prime of x is derivative is always less than 5, equal to 5 or less than 5. If function is differentiable, function is continuous. That's we good. And now the question is, how large can f of 2 possibly be? Okay. And you probably saw it. I have the nice solution, the rigorous solution. But what we can do, we can basically try to draw the situation, and without any computation, because we can definitely apply the mean value theorem, and I can show you. Where was my room? Okay, I have the room here. But I would like to check something. You will tell me the answer. Okay, because you remember, we have to fill it. Okay, what we have? F of 0 is -3. F of 0, actually, f of 0 is here, -3. That's 0. Now we're looking at f of 2. And we don't know where is f of 2. Here, 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 I don't know. Yeah, I don't know. But we know that when I connect these points, let's pretend it's here. Yeah, of course, I don't know. Could be lower, could be higher. F of 2. I don't know where is that dot. I'm just pretending that f of 2 is here. If we will get different value, it's fine. But I mean, I don't even, yeah, I'm just, because we're looking for f of 2. Okay. But what we can use, we know that this average rate of change, the slope of this line that I just draw, is actually the same like the slope, like the derivative. And since they're asking for how large could be f of 2, we have to find the largest value of 2. What is the largest value of the slope? What is the largest value of this derivative? Derivative is 5 or less. That means 5 is the largest value. This is telling us derivative, but this is also telling us that this is that slope of that tangent line and that secant line. It means slope of this line, the largest slope that we can get is 5. Other one is less than 5. If we know the slope is 5. We also know how to get the slope, rise over run. Run, of course, is 2. Oh, let's be more professional. Delta x. Delta x is 2. Delta y, we don't know. But let's do this one. In order to get slope, right, we will divide delta y over delta x. It is 5. Rise over run. Now, we don't know what is that rise. We don't know what is delta y. But now, what value divided by 2 will give us 5? Can you tell me what number divided by 2? 10. That means the distance, the rise distance between -3 and f of 2 must be 10. This is 10. Because 10 divided by 2 is giving me slope. If this distance is 10 and we starting 3 units below the x-axis, how far we can rise above the x-axis? The blue vertical line must be 10, the line segment. Can you tell me what's the value of 2? Yeah, we can see that we have to have 10 and we have 3 units below. We have 3 units below the x-axis, 7, done. Yeah, as we can see, we don't, and this actually, we did use the mean value theorem because I used that slope. And let's see. I, of course, have the proper way, but if we understand this picture, that's what I need. F of 2 minus f of 0, because we're dealing with the points 2 and 0. And then f of 2 minus f of 0 is -3. And of course, I did substitute 5 as a maximum value of that slope. Then I will get the maximum, the largest possible value of f of 2. And when I multiply by 2, 10 subtract 3, it is 7. Yeah? Oh. But we manage, based on having the run, the changes in x, and having the slope, we can figure out the 10. And since we have -3 plus 7 will give us 10. I mean positive, I mean 3 units below, 3 units below. Yeah. Okay. That's something, yeah, that we can also. Why this is 7? Because who is asking? Christopher. Do you understand, Christopher, where we got 10? Do you understand? Because yes, okay, good, excellent. Because we know that this is slope. We didn't know 10. Yeah. And I ask, like, what number divided by 2, because that's the slope definition, what number divided by 2 will give us 5? Of course, 10. And now, if this distance is 10, and this distance is 3 units, what's supposed to be the distance above the x-axis? If this is 3, the entire distance is 10. Yes. Okay, this has to be 7. Yes, okay, good. Of course, we have to, yeah, and that's the reason. We also have a nice rigorous definition, and yeah, but